Okay, now sing. Go ahead. We're streaming now.
Are we streaming?
We are streaming. Go sing.
Alright.
Who knows? Maybe you'll be on one of those talent shows.
That's my nightmare. Living, waking nightmare.
Just the next season.
In one of the talent shows?
Oh, yeah.
Oh man, that thing is noisy. I could hardly hear myself talking. And that's without actually using words, just the inside loop itself.
Oh, it sucks.
I cannot even hear all my voices. I can hear about two.
It's got cold all of a sudden, man. It surprised everybody. Last night I was driving home and all of a sudden my temperature gauge, or my indicator just starts flashing because it says, oh, there's a road hazard of icy roads now. It's so cold.
Yeah, it was icy. That's for sure.
And that was just in the 50 in town.
Oh, really?
Yeah.
Oh.
Okay, maybe a little bit east of Sacramento. But like, before I got to Rancho.
Still, it's in Sacramento. Alright, come on. I know the internet connection is there. There we go.
I think the last important thing to talk about was latency.
That was for the test review, I think.
That's for the test review. So I'm looking for stuff that we talked about before the review.
Oh, Mantissa and the exponent.
I know, but how far did we go in that module? So let's check it out.
I remember you expressing the thing as a what's it, hexadecimal, and you're looking at the values in the sign bit and the exponent bit.
I think I can probably tell by which lab we are on. So we did part 2, right? Pretty sure we did.
Yeah.
So we did part 2. So that means we probably have completed to talk about most of the issues related to conversion. Okay. So tonight's lab is going to be a continuation of this, but it's actually a program that you guys have to write. But I'll give you guys a week to do it, so it's not like you have to complete writing a program in 1 hour and 20 minutes. So we'll get to that when we get to that. Okay. But are there any questions related to floating point number discussion as of last week?
Yep. I didn't really understand the process of how they were converting the base 10 exponent to a base 2 exponent.
Oh, okay. So let's go ahead and do that. Okay. All right. So to talk about that, I think it's probably best if I use my tablet. So let me.
I think I have a rough idea how to do it, but I wonder if it's an easier way or if I'm thinking of something.
Well, tonight's lab is actually related to that, so we can touch on that a little bit. I have to be careful with how I use the time in this particular section because we are already 2 days behind the Tuesday-Thursday class. Not because of us being slower in this class, but because we lost 2 Mondays.
Right.
Yep. So that is not, it's not helpful. Okay, let's do it one more time. Yeah.
Oh, because this class started a day late, huh?
Yeah, this class also lost the Monday on the week. Yep, on the first week. Oh, finally. That noise is just, horrendous. Okay, so let me let me get rid of these windows first. Get rid of it. And 310. This is Monday, Wednesday. Yep. And the worst part is, we are meeting one day, and then, and it has been a week since we last met. Okay, and then we will meet again on Monday, which is 5 days later. I really hate intervals like that. Okay, so let's talk about base conversion. Okay, so we have a mantissa. The mantissa can be any value. Okay, it doesn't really matter whether the mantissa is expressed in base 2 or base 10. because the mantissa is just a quantity. So the question is, what is it a quantity of? Okay, that becomes the question. In a base 10 scientific notation, when you use a calculator, it is expressed as a power of 10. So we have exp10, exponent of 10, specifying, oh, okay, we're expressing units. We're expressing in units that are powers of 10. So eventually we want to convert this to something that is expressed in units of powers of 2. But there's no one is saying that we cannot have them both at the same time. So we were basically looking at something that looks like this all the time. Okay? When you have the base 10 version, the only difference is when your number is expressed in base 10 as a base 10 scientific notation, exp2 is 0. Right? Because anything to the power of 0 is just 1, so it does not matter. Okay? So what we want to do is to start with a non-zero exp10 and eventually get exp10 to 0. But to do that, you will have to adjust something in exp2. So that's the whole idea of the base conversion process. Is somehow we have to get rid of exp10. If it's a negative integer, we want to bump it up eventually to 0. If it's a positive integer, we want to decrement it so that eventually it also gets down to 0. Is that okay? So we'll play out a few scenarios, okay? And this mantissa is not going to be normalized, okay? So we can assume that the mantissa itself is already an integer, because the whole purpose of that conversion process is we want to avoid the use of floating point numbers, because otherwise it becomes kind of like a chicken and egg problem. Is that okay so far? Okay. So we'll write down these assumptions. M is a 64-bit unsigned integer. Okay? Because we can always adjust the powers of 10 and the powers of 2 to make it normalized. So normalization is not an issue. We can always move the decimal or binary points around until m is normalized or until m is an unsigned integer. So that part is not an issue. Is that okay? But we have two cases. Okay, so you have to basically look at two cases. One case is when exp10 is less than 0. The other case is when exp10 is greater than 0. Because when exp10 is less than 0, we want to increment exp10 somehow so that exp10 becomes 0. If exp10 is greater than 0 to begin with, we want to decrement exp10 until it becomes 0. So in today's class, we're just going to deal with one. Okay, we'll deal with the left branch. So if you look at just the left branch, then we are basically asking the question of how do we increase exp10, right? Because this branch corresponds to when exp10 or the exponent of 10 is less than 0 to begin with, and we want to bring it up to 0 because that means we are done. We are done with the base conversion. So how do we do that? How can you change the exponent? What can you do to the mantissa to let you increase the exponent? We want to maintain the value represented, which means I cannot just blindly add 1 or add whatever number to exp10 because that's just increasing the value. So I have to do something to the mantissa to cancel that effect out. Huh?
Move the decimal.
We have to move the decimal point, yes, but that boils down to what kind of operation? Huh?
Divide by
Division by 10. Very good. Okay. So so what we're looking at is something like this, okay? So we can say something like this, m divided by 10. Then we can say, we can now say the exponent of 10 is the old exp10 plus 1. And then the two exponents can remain the same, which we don't know at this point. Okay, it can be any number. Okay, so if I call the value represented v, okay, so let me be more complete here. If I call this v, okay, v is the original mantissa times 10 to the power of exp10 times 2 to the power of exp2. Do you think I have preserved the value by doing this expression here? By dividing the mantissa by 10, but I also increase 1 in the exponent 10. Would that preserve the value? Okay, it should, right? Because increasing the exponent of 10 is the same thing as multiplication by 10. That will cancel out the effect of division by 10 in the same product. Is that okay so far? More or less? Okay, this is the kind of math that I'm expecting people to understand coming into this class, because it really is important in this type of representation. Okay, but I only have one problem with this approach. Division by 10 is an issue, especially when m is a small value. Because I want to represent everything as integers. I don't want fractions. I don't want floating point numbers. I don't want fixed point numbers. I want real integers. Okay? So if m is a small number, like 25, 25 divided by 10 is what? 2.5. But since integer division does not give you the 0.5, what does it give you instead?
2.
Just 2. So the 0.5 out of 2 is what kind of percentage? We're talking about 25%. So the error is 25%. That is not okay. All right. So how do we decrease the amount of error? Let's think about 23 instead. Okay, 25 is kind of not such a good number to think about, but 23. Let's talk about 23. So 23 divided by 10 is 2 in integer division, but it really should have been 2.3, right? So 0.3 out of 2 is what? 15%. Still not acceptable. That's still way too much. So what can we do to adjust the error that we can? How do we minimize the error?
Not use integers.
Bigger integers, right?
Yeah.
So if you multiply 23 by, let's say, 16, okay? 23 times 16 is what? 23 times 16 is 230, and then we got 8138, so we have 468. Okay. If you divide 468 by 10, the integer version, okay, so let's do it, right?
Shouldn't be
368.
368.
Is it 3?
Yeah.
Oh, okay, yep. Thank you. Details. Okay, but the point is the same, okay? So we are looking at what is the error. This really should be 36.8, right? That is the actual result. When you look at the integer version of this, it's only 36. What is 0.8 out of 36? It's less than 15%, right?
Yeah.
Okay, so that's just by multiplying 23 by 16. What if I multiply 23 by, let's say, 256? And then do the division by 10. Well, the error is going to be even smaller. So what we want to do, okay, if you go back to the tablet, is we want to do this we want to do something like this. Okay, we want to say m times 2 to the power of something. We'll just call this p, okay? Divided by 10, because this will minimize the error that we're dealing with. Times 10 to the power of exp 10 plus 1, because we still want to adjust the exponent of 10, okay? One step at a time, just one at a time. But this time, when we deal with this 2 to the power of exp, I have to kind of be careful, because we are multiplying 2 to the power of p to mantissa before we do the division by 10. We have to kind of cancel out this effect of multiplying by 2 to the power of p. So how do I counteract the multiplication of 2 to the power of p to the mantissa? What can I do to adjust the exponent of 2 so that this number is v again? So we have to subtract p from
The exponent of 2.
the exponent of 2. Very good. Okay. So is that okay so far? And we are trying to maximize this p. We're trying to find the largest power of 2 to multiply to m So before the division by 10. Does that sound familiar to you? I sure hope so, because that's what we did a week ago. One of the questions, at least one of the questions, was asking about this p, this power of 2. Is that okay? All right. So what kind of p are we talking about? What do we want this m times 2 to the power of p to be? In other words, when I look at this product, what is the limit? How far can I bump it up? But this is from an implementation perspective. It's not from a mathematical perspective. From the implementation perspective, when you write a program to do this, don't we have a limit? What kind of limit are we talking about?
64 bits.
So it depends on the width of the integer that we use, right? So right now, 64-bit seems to be reasonable, right? So we want m times 2 to the power of p to be as large as we can store using a 64-bit unsigned integer. Is that okay? Once we find out what that p is supposed to be, then we perform this multiplication, and then we do the division, but we also want to decrement exp2 by that much. But once we do the division by 10, then we can also adjust exp10 by 1, but just 1, because we're dividing by 10. Every time you divide by 10, you can bump up the exponent of 10 by 1. Is that okay? So what we are really trying to do now, there's one more thing, okay? Because when you look at integer division, and this is from one of the questions from last week's lab too, when you do integer division, it's always truncating, okay? But truncation is not always your friend. When you look at 2.7 divided by 10, okay, well, yeah, we can look at 27. 27 divided by 10. The correct value is 2.7, but if you want to do rounding, it should have been 3, okay, so we call it approximately 3. But the truncation is always doing the floor function, so you're taking the floor of 27 divided by 10, which is 2. In other words, after an integer division, you always end up with a value that is smaller than what the result of the division is supposed to be.
Smaller or equal to.
So it's biased. Okay, so we call this kind of error biased, B-I-A-S-E-D, biased. It is always smaller. Now, when you look at 2 to the power of 63 plus something divided by 10, yeah, we're talking about a very, very small error. But if you keep doing this many, many times, the errors will add up, and they all add up in the same direction, which means the cumulative error is going to be significant because they're all leaning to one side. So that's why we need to do rounding. Okay. So what do we do when we do rounding? How do we do rounding with something like this? It's one of the questions. We add 5 to it first, right? So the rounding of x, which is an integer divided by 10, is the floor of x plus 5 divided by 10. So that's why we need to add 5 to it first. Okay? Because this way, yeah, we are not making, this plus 5 has nothing to do with making the error of each division smaller. It has to do with making the error not biased. Sometimes it's smaller, other times it's bigger, and hopefully they all kind of even out. Is that okay? So the plus 5 or the rounding is for eliminating the biased nature of division by 10, by integer division. Is that okay?
Oh, so it kind of like puts the number closest to the middle and then lets it go.
Yeah, so you still have an error, okay? Every single time you do a division, so let's say this pen is the correct answer. So you will still have a little bit of error, sometimes on this side, but other times it will be on this side. So it goes back and forth like this, so you don't have a cumulative error that is always leaning on one side and it keeps multiplying the error that you have already accumulated.
It normalizes it like we would round on math, like we were doing a
Exactly. Yep. But it will make it so that it's not always going to one side. So that is why we had that question in last week's lab activity. It's because I want you guys to understand what it is, but now we understand why we need to do it. Is that okay? So getting back to the tablet, that plus 5 is just there. So we have to add the 5 to the product of m times some powers of 2, and then divide the whole thing by 10. Whatever that thing is becomes your new mantissa. Okay? And then your new exponent of 10 is 1 more than what it used to be. The new exponent of 2 is p less than what it used to be. And then you maximize, you just repeat the whole cycle. Okay? So let me just finish this slide here. So after this operation, so what this operation really is m gets updated to become m times some power of 2 plus 5, the whole thing divided by 10. exp10 is updated to be exp10 plus 1. And then exp2 is updated to be exp2 minus p. When you're done with all of this stuff here, go back to the beginning and see if you have to do it one more time. Basically, after this entire operation, you check your exp10 again to see if it is still less than 0. If it's less than 0, do this whole thing again. Find another p. Okay, so p can change, from one case to another case. You're really just trying to find the p that will maximize m times 2 to the power of p, so that it is just barely less than or equal to 2 to the power of 64 minus 1, which is the largest value you can represent as an unsigned integer using 64 bits.
Is that 2 divided by p? I'm confused.
Which part?
Right there. V equals m equals 2 blah 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 times 2 exp2 divided by p.
Divided by p?
No, it's minus.
It's minus.
Oh, I'm sorry. It's just a bit lopsided.
Oh, bad penmanship.
Well, you're drawing with a mouse. I don't blame you.
No. I'm just drawing using a stylus.
Oh, never
So
mind
no
then.
excuse there. Yeah. So we're doing okay so far with this approach. How do you find this p then? Remember, you cannot use log. You cannot use power. Those are all floating point calculations. So how do you find p? You can use a loop. So how do you use a loop to find the largest p that is still making this product within the range of a 64-bit unsigned integer?
The do while loop?
A do while loop? No.
Oh,
Just a while loop.
okay.
Because you might have m already satisfying that requirement. So p would be 0 in that case. You don't have to adjust it anymore.
But you need to test at least once, though.
Yep, you need to test it at least once. So that means a while loop, not a do while loop.
Alright.
A do while loop is going to do it once and then check the condition. So that's not, it's almost the same, except you want to avoid that. Let's do it at least once because you want to check first.
Okay.
Okay? So what do you do to double check and make sure that your m times 2 to the power of p, okay, expressed in a certain way, is still too small and you can make it bigger? How do you check that? Do you guys remember there was one question where
Need the 64
X.
bits.
exactly x has to go within a certain range?
Yeah.
Right? It's the same thing here. You want this product, m times 2 to the power of p, to be at least 2 to the power of 63, and no more than 2 to the power of 64 minus 1. Once it gets into that range, it's time to stop. Now, when we check whether a number is within a range, normally, there are two ways to be out of range, right? You can be too small, you can be too big. But in this case, you only got one side of out of range, being too small. There's no way it can be too big, so it can only be too small. Is that okay? Are there any questions? You first and then you. Yep.
What was the range? You said m to the 63rd. It has to be greater than m to the 63rd, but smaller than m to the 64th.
Okay, so when we take this value, okay, I'll give it a name so that we don't have to keep calling the product itself. So x is this quantity. X is m times 2 to the power of p. Is that okay? So the objective is we want x to be at least 2 to the power of 63 and less than or equal to 2 to the power of 64, the whole thing minus 1. That is the range that we want it to be in.
Okay.
Okay? But this range checking seems to imply that, oh, x can be too small, x can also be too big. But we actually don't have to worry about x being too big, because 2 to the power of 64 minus 1 is absolutely the largest value you can represent using a 64-bit integer. So x can only be too small. In other words, you don't even have to worry about this side of the comparison. You only have to worry about this side of the comparison. You only have to deal with the 2 to the power of 63. In other words, this is the only part that you need to check. When x meets that requirement, get out of the loop.
And what did you say x represented m to the power of p?
Yes. So x is defined to be m times 2 to the power of p, but that's only for mathematical use. Okay?
Okay.
Which means when you're implementing a program, you can keep multiplying m by 2.
Okay.
Multiply m by 2, well, check first, okay? If it's still too small, multiply by 2 and assign and update itself, check again, and then keep doing that. But you have to keep track of how many times you have do it. You have been doing it because you have to update exp2 by the same amount of times that you have gone through the iterations. Is that okay so far? So that is how we do base conversion. Okay. Ultimately, it is done by the division by 10. But before we do the division by 10, we have to maximize the numerator to minimize the error. So the trick is, how do we maximize the numerator? Well, keep multiplying by 2 until it is at least 2 to the power 63. So how do you specify the condition? There are many ways to specify that condition, so I'm going to leave it up to you guys to figure that out. Okay, how do you specify the constant of 2 to the power 63? And there's also another way to do it, using a bitwise operation, because anything that is within this range, guess what, has bit 63 being a 1. So you can check bit 63, but you can also actually do a real comparison to the constant, which is 2 to the power 63. But you cannot use power, which is a floating point number. So how do you specify 2 to the power 63? You can use a calculator, right? No, because your calculator has a problem. Your calculator can represent values up to and exceeding 2 to the power 63, but it doesn't have the precision to do it, because you need 18 digits to specify that actual exact amount. Your calculator is not going to give you 18 digits. So you have to figure out a way to specify that quantity, and there are many ways to do it. Bitwise AND with bit 63 is one way, okay? Bit shifting is the other way. Using a hexadecimal representation to represent 1 followed by 63 zeros is another way. And it keeps going and going and going like that. So is at least one of those 3 methods familiar to you? Yes? Okay, I'll repeat one of those three methods. And I'll even write it down. Okay? So you can use bitwise AND to check bit 63. Okay, we talked about bitwise AND already in this class. So, and indeed, we had one lab that was working on bitwise operations. So, bitwise AND, you can look it up too. If I don't talk about bitwise AND, what are you going to do? You cannot, well, I guess in the class you can just say that, oh, Tech, you have never mentioned anything about bitwise AND. But if this is in your job, what are you going to do? Exactly. You cannot just complain to your boss and say, "Boss, you never explained what is a bitwise and I cannot do this," right? The boss will go like, "Okay, let me just pick one more job application from my stack," right? So you have to look it up. If it is not familiar to you, look it up and find out what it is. Bitwise AND is not a mystery. It is not difficult to understand. You just have to look it up. It is a standard operator in C and C++. Okay? So that's one way. Second way, how do we represent 2 to the power of 63? Okay? You can use hexadecimal. Okay? Because once you know what it looks like in binary, you can use a hexadecimal number to represent it. One hexadecimal digit is going to represent 4 bits. So you look at that 64-bit number. Okay? Now, okay, as a hint, you don't have to write the entire thing out, okay? So you don't have to write out 1 and then followed by 63 zeros because it's a pattern, okay? So you look at that whole thing and you say, okay, I want to convert it into hexadecimal. You group the bits by 4, groups of 4, and then you do the conversion like that. So the most significant digit is going to be 1000. Look up the table. Which hexadecimal that corresponds to it? Next 4 digits, guess what those are? 0000. And which digit in hexadecimal do you think corresponds to 4 binary zeros? 0. Thank you. The next 4 digits, what do you think they look like?
0.
The next 4 digits, what do you think they look like?
0.
So the only mystery is what corresponds to 1000 as a hexadecimal number. I'll let you guys figure that out. Okay? That's the second way. Third way is don't even bother to express the constant entirely and use bitwise or bit shift operation to specify that quantity. And I'll give you one big hint. Use left shift, not right shift. Okay, because when each left shift operation is the same thing as multiplication by 2. Okay, so I'm not going to tell you how many times you have to shift, because we have to specify 2 to the power of 63 to start with 1. So how many times do you have to multiply 2 to 1 to get to 2 to the power of 63? That's the number of times you have to shift. Is that okay? So there are at least these 3 methods to do it. Pick one. All right? So I'm leaving this as a puzzle for you guys to solve because, it's part of the exercise. Are we doing okay so far with this? All right. So that handles the case when exponent 10, the exponent of 10 was less than 0 to begin with. So if I go back to the decision tree, what about the other branch? What about this branch over here when exp10 was greater than 0 to begin with? What am I going to do?
Yeah, decrease.
I have to decrease it. So how do I decrease the exponent of 10? The math works out to be about the same as what we have to do now. So I'm going to use a new page, and I'll repeat what the condition is. What if exp10 is greater than 0 to begin with? What are we going to do? We have to decrease it, right? And I'm going to repeat the v equals to the original mantissa times 10 to the power of some exp10, which we know is positive, times 2 to the power of some exp2, which initially is 0. Okay. The objective is to do something like this. We want v equals to some expression here, which I'll express later. And the objective is we want the exponent of 10 to decrease. Okay? Possibly at the sacrifice of some modification to exp2, but we don't know what it is yet. So there's something we have to do to exp2. So this is the template, okay? But the focus of this template is we want exp10 to decrease by 1. How do you decrease the exp10 by 1?
Multiplying it by 10?
Yep, the mantissa needs to be multiplied by 10. Okay, very good. So we say, okay, let's multiply the mantissa by 10. Okay, which is fine up to a certain point. Why do you think this is going to be okay? But at a certain point, it may not work anymore.
64 bits again, right?
Yep, you have 64 bits. So if you keep doing this every time you decrement one from EXP10, at some point this product, okay, because you keep multiplying 10 to m, right? It gets bigger and bigger and bigger. At some point, you can no longer contain 10 times m in a 64-bit unsigned integer. Then what are you going to do? When this amount is too big, what is your option? You have to sacrifice something, right? When this amount is too big, then what you need to do is to subdivide it by some power of 2 so that it remains within the range that you can represent using a 64-bit number. But when you do a division like that, you have to adjust the exponent of 2. A division by 2 to the power of p,
Add 1.
you have to add p
Oh.
to exp2. So you got the right direction, it's just the wrong quantity. There we go. Is that okay? What if 10 times m is still within the range that I can represent using a 64-bit integer? P equals to 0 then. It is not a special case, it simply means that p equals to 0. That's all. Okay? What about that rounding thing? Do you think division by 2 may have issues with rounding? Absolutely. Okay? Because every time you divide something by 2 in an integer division, it can be exact, it can also be missing 1, right? Because the remainder of division by 2 can be 1. So that means the whole thing about integer division has a bias to make the result smaller still applies. And we still have to do rounding. How do we round this?
Same way than +5?
Plus 1. Yep, plus 1 divided by 2. Okay, but I'm not going to write it here because plus 1 divided by 2 only applies when you're dividing by 2 itself. It does not apply when you're dividing it by 2, any random power of 2. So I'm not going to add a plus 1 here. Okay, so now the focus is to figure out when do we need to divide it by some power of 2, and what power of 2 should we divide before we multiply m by 10. Is that making any sense? You cannot check, okay? So let me repeat. Do not check whether 10 times m is greater than 2 to the power of 64 minus 1. That will not work. Why can't this work? Yep, exactly, because 2 to the power of 64 minus 1 is absolutely the largest value you can represent using a 64-bit number. So if you check something like this in your code, it is always going to be false. So we cannot do it this way. Okay, if that is not something that we can do, what else are we going to do? Same condition, we want to see if 10 times m is going to exceed the range that we're dealing with.
Well, the moment it goes past 64 minus 1, it's just going to start at 0 again. So
Not necessarily, because this is a multiplication. If you're adding 1, yes, when it overflows, it goes back to 0. But this is multiplication by 10. So what are we going to do? Let's do some algebra. Yep.
Can you check how many times you multiply by 10?
You keep track of how many times you have multiplied by 10?
Yeah.
And how is that going to help? Because your m itself can change depending on what number you start with. So that's going to work. That's not going to work either. What about some algebra? Can we check something like this? That we can do, right? Because 2 to the power of 64 minus 1 as a numerator and then having 10 as a denominator, that number is well within the range of values that we can actually represent using a 64-bit number. So we can check whether m is exceeding this. Does it make sense?
Yeah.
Okay. So what if m is exceeding that range? What are we going to do? Okay, so if m is in fact, more than that, then we should not multiply m by 10 anymore, right? First consequence, right? Because if we multiply m by 10 at this point when this condition is true, then the product is going to exceed what we can represent using 64 bits. So what do we need to do first before we multiply 10 to m? We have to make it smaller, right? How do we make it smaller? Divided by 2. Very good. Okay. So then we have to check and ask the question. This is asking the question. Then we say, okay, let's divide m by 2. And then we ask the question, is that going to be still too much? Okay? So we're dividing by just 2. And what do you do to round when you're dividing something by 2?
Floor?
No. Well, the floor is implicit in any integer division. Add 1 first. That's it. So you perform m plus 1 divided by 2, whatever that thing is, you compare it to 2 to the power of 64 minus 1 divided by 10. What if it's still too big? Do it one more time. If that's still too big, do it another time. Do this until this number, this value, is no longer greater than 2 to the power of 64 minus 1, the whole thing divided by 10, because then you have room to multiply that thing by 10. Is that okay? I'll write it down here. So when m plus 1 divided by 2 is less than or equal to, okay, I shouldn't say that. Back. Okay. So when m itself is less than or equal to 2 to the power 64 minus 1, the whole thing divided by 10, but then you have to be careful because you have to add a 5 first, because we are dealing with rounding. Okay. Actually, I take it back. Let's not do this. This is safer. So when m is less than or equal to this constant, then you have the room to multiply it by 10. And when you multiply m by 10, then you do all the other adjustments. Is that making any sense? More or less? Just the strategy itself, okay? Because the objective is we want to make exp10 0, and it's positive to begin with. But every time you decrement exp10, you have to multiply the mantissa by 10. But if you keep multiplying the mantissa by 10, there's a potential that it can be out of range. So when it is out of range, this condition will be true. M is greater than 2 to the power of 64 minus 1, the whole thing divided by 10. So when this happens, then you have to say, I'm going to keep using this operation to update m until m is less than or equal to 2 to the power of 64 minus 1, the whole thing divided by 10. Then we can actually do the multiplication by 10, adjust exp10, and then you go back and check again to see whether exp10 is still positive. Is that okay? Tonight's lab does not involve this part, it's only the other part. So this is something that we can do sometime next week, probably next Wednesday. But is the general strategy understood? Okay, there are only so many things that we have to do. Division by 10 is going to help you increase exp10 until it becomes 0. Multiplication by 10 will decrease exp10 so that if it's positive to begin with, eventually it will get to 0. But you have to make sure that your mantissa is as large as possible, but not too big. So you have to multiply the mantissa by some power of 2 to make it as big as you can, in the previous case. In this one, you have to divide it by 2 occasionally so that you have the room to multiply m by 10 again. So that's the general strategy of doing all this stuff. And then within all this, we have the rounding issue. So every time you do a division, you have to make sure that you take rounding into consideration. And that's it. That's basically the essence of how you convert a base 10 scientific notation to a base 2 scientific notation. The normalization part is actually pretty easy, so I'm not even gonna talk about it today. All right, any questions? No questions? All right.
So there's always a % error, right? No matter
There's
how-
always an error. There are certain numbers that cannot be represented exactly.
So that's why my calculator, once it gets into the exponents, gets a little funky. Very hyper. No.
Right. So the issue with a double precision floating point number has to do with the actual precision part is only 53 bits. So if you're trying to represent a value that is more than what 2 to the power 53 minus 1 can represent, then it's not going to represent that value exactly anymore. It's going to be representing that value as an approximation. And that approximation, guess what, is basically some integer that is between 2 to the power 53 and 2 to the power 54 minus 1 times some powers of 2, which is something that we talked about or in the previous lab. So that's why certain values cannot be represented exactly. Is that okay? All right. So we are moving on to the next topic, which has to do with memory devices or the von Neumann architecture. So we still have more labs to do with binary floating point numbers. In fact, let me import the quiz from the other class first so that you have the activity tonight. So this is how I make new lab activities. So we just say this is a new quiz, this is a lab for negative EXP10. Huh? Okay, it was the cursor, right? Yep. And then once we add it, we can just go back and edit when it's going to be due, and so on and so forth. This is actually harder than using Moodle.
Moodle?
Moodle, M-O-O-D-L-E.
What's that?
It's another course management system that I have been using for many years. And then one day the district said, no, TAC, you have to move on and use Canvas.
It's the way of the future.
Hmm?
It's the way of the future.
Not exactly.
Someone got paid, that's what happened.
That's it, exactly.
Okay, I'll put it this way. Canvas is like a Prius, okay? You get in, you turn on the ignition, it goes, okay? But you can't really do donuts, okay? You cannot drift. You cannot really, it has no handling whatsoever. Okay, there's no joy in using it. It gets you from point A to point B most of the time.
There is no joy.
Yeah. Moodle, on the other hand, is like my car. I have a Miata.
Nice.
Yeah, it's a stick shift. If you want to go to 65 miles per hour in second gear, sure, why not? It's your car, it's your engine, your motor oil.
Right. I can change that.
If you want to drift, just get a limited slip differential and make your donut torque to break loose anymore. Because the tire's already worn out, right? it takes a 1.3 liter engine, just a little bit more gas to break loose. So when you hear those squealing sounds in a parking lot, just kind of remember that. So it's going to be 28 at the end of the lab is 9:50. Okay, and it's going to be available from now. So this is 21st. Let's make it 8:20 p.m. and until that I will talk about this lab in tonight's lab time too. Even though it is just a programming activity, the way you want to set it up is a little bit different from all of your other labs, because you have to make sure that you have a platform where you can actually write code. So it's going to be a little bit different.
Oh, I thought you were just gonna make the whole lab right.
Huh?
I thought you were gonna make the whole lab right now.
Nope. I'm just setting up the questions, so by the time we get there, you guys can just sign in and start with the instructions. All right, so that's done.
Can we access the previous labs in preparation for the test?
Can you? Have you tried?
I haven't tried.
I think you create a duplicate so you can access.
I have not yet
Oh, you
done
have
it.
not.
So I can use tonight's lab to do it if I don't have a lot of questions.
Good thing I asked.
Yep, good thing you asked. All right, so we are moving on to D flip-flops and basic memory devices. We only got about 25 minutes left, so that it's not enough time to really get into the, well, I guess we might have some time to do it. But the first thing is, who's von Neumann?
It sounds German.
It's actually Hungarian, but close enough. Okay, I hope no one is actually Hungarian in this class and they go like, no, we are Hungarians, we are not German. Not the same.
True.
The lab's due on the 28th.
Yeah.
Oh, okay.
You have 1 week to work on it. It's a programming assignment, basically.
Oh.
Yeah. So you got a week to work on it. That should be enough time, based on what we have already talked about in class today. Okay, so we want to look it up. Okay, so we look up who's von Neumann. Okay, and the first link, which is a Wikipedia link, is good enough. Okay, that will show you.
They fake it?
Hmm?
It's not fake?
It's not fake. I can tell. This is the guy. So this is John von Neumann. Okay, he is many things. So his expertise include all of the following. Okay, so this is just including. It's not an exclusive list. So he is an expert in mathematics. Not really surprising, because computer science is a branch of math. But within the branches of math, he has foundations of math, functional analysis. What is this? Ergodic theory, representation theory, blah blah blah. And he also knows his physics stuff, quantum mechanics, hydrodynamic, quantum statistics, mechanics, economics, computing, linear programming, self-replicating machines, and statistics. And the amazing part is he's not your typical jack of all trade, where what is that phrase again?
Jack of all trades, master of none.
Master of none. He's master of all. In fact, there are other articles that talk about him and how it's recognized within the mathematician circle. All the mathematician geniuses or genii will recognize him as the mathematician at the time. And then you ask all the computer science people, they would say that he's the genius of the time.
Isn't this the guy, like, at age 5, he could, like, divide two 13-digit numbers in his head?
I do not know that factoid about him.
I just read
I would
something
not be
about
surprised.
that, like, the other day.
Yeah, I would not be surprised. Unfortunately, like Alan Turing, he is relatively short-lived. So you can see that he only lived 54 years. Okay, a little bit longer than Alan Turing. Alan Turing died in his 40s. But he only lived up to his early 50s. But in his case, he did not commit suicide. He had cancer, which most likely is the result of him participating in the hydrogen bomb experiments. So, because he understood the quantum physics part, he understood a lot of physics, so he was actually involved in the development of hydrogen bombs, along with the von Neumann architecture and whatnot. Okay, so interesting history. He's also in the same timeline or the time span as Albert Einstein. They both taught at Princeton University at the same time, once. Okay? Now, Albert Einstein is what you call a typical or classical INTP in terms of personality type, introverted. Okay, the key part is introverted. And Einstein liked to work by himself, alone, without a lot of distractions. This guy likes to listen to polka music when he's working, loudly.
No.
Huh?
He's Hungarian.
He's Hungarian, yes, exactly. Yep. Well, Albert Einstein is Jewish. I'm pretty sure there's loud music, in every culture. Yeah, but so he used to bother, Albert Einstein quite a bit because, down the hallway, a few offices, here comes, these blaring, polka music. But he is interesting. I'm pretty sure along that hallway they had a lot of interesting conversations because one of the things that von Neumann is really good at is quantum mechanics. And guess what Albert Einstein did not believe in?
Quantum mechanics.
Quantum mechanics,
Because
yes.
everything had to be deterministic.
Yes, because God does not play dice.
Exactly.
Okay? And then this guy keeps yakking about how, we all throw dice, whoosh, like that. Yep. So, interesting person, if you have time, I would definitely read the rest of this article because, he's one of those really, really, really rare geniuses who's good at many, many things. I mean, Albert Einstein is a genius too. Okay, his view of, the speed of light is constant and everything has to adjust to account for that. I think that is brilliant. Okay, that's way out of the box type of thinking. But this guy's good at many fields, and he has innovative ideas of a lot of things that he's on this list. So that's kind of important. Okay, but getting back to computers, right? So what is his contribution to computer science? In other words, without him, what kind of computer will we be using today? That's the question.
Statistical mechanical.
Okay, so when was the last time you updated your apps and your phone's firmware?
This morning.
It does it by itself, right?
Yeah.
Possibly, once a day or something like that.
Every time I plug it in.
Pretty much.
Yep. Okay, so that's kind of cool, right? You don't have to do a single thing. Your phone actually does it all by itself, and that's because the software or the instruction of what the program needs to do is stored in memory. Okay. To us, that's kind of like, how else, how else is my computer going to know what to do, how to carry out the operations, right? Of course, the instructions are stored in memory. Well, before him, computers were not designed the same way. So computers had memory because when you're trying to solve for ballistic solutions and stuff like that, you need storage to store the numbers that you're working on. Okay, when you're trying to do integration, you need a number to do all the summation and stuff like that. Okay, you need an index to go from one place to another place and stuff like that. So we do have memory in computers before his time. What is interesting is the specification of what to do, the instructions, were not stored in memory. There's no such thing as instructions per se, because computers were hardwired. You literally connect wires from components to components to components to specify what to do in the computer. So when we update our programs, okay, when those computers were updated before his time, it literally involves taking out the panels of computers and unwire a whole bunch of stuff and rewire a whole bunch of stuff. And we are talking about computers that has the complexity of maybe 1/100th of my Fitbit at the most.
The size of aircraft carriers.
Yeah.
My grandfather used to work on one.
Yeah, but your grandfather is probably still after von Neumann.
Exactly.
Yep. So think about it this way. Without von Neumann architecture, which simply says, hey, we can store instructions in memory. Okay, we can get the instructions, we can figure out what to do next from memory locations. Without that insight, there's no such thing as updating your app automatically. To update your app, okay, just imagine this. You have to get a microscope, open up the back of your phone, undo millions and millions and millions of wiring, and then look up the schematic of the new app, and then rewire those millions and millions and millions of tiny little wires. If you miss one, it's not going to work. That is his contribution to computer science. And I would say that's a pretty significant one. Okay? And it is also, at least at the time, it's a quantum leap. Okay, no pun intended. But it was a very important leap from saying, oh, instructions or how things should be done should be just hardwired. Instead of doing that, it's now stored in memory. So that's why, in this particular module, what we're going to do is we are going to focus on the discussion of memory, how memory is organized in a computer, and how do we utilize that so that we can store programs or instructions in a computer. We can store instructions in RAM, which is then used to feed the processor, so the processor can figure out what to do. So what we'll do now is to take a look at some of the really, really small memory devices, which probably does not even resemble memory from your perspective. In fact, we can benefit a little bit from the other class, so we'll take a look at the SR latch first. This is called the SR latch. And what do you notice about this circuit that is kind of different from all of the other circuits that we have talked about in this class? And that includes the 3x3 carry look ahead mechanism and whatnot. Yep.
The output of each gate is an input to the other gate, so it's like reliant on each.
Yep.
On each gate.
Yep. So there's a feedback mechanism, right? So when you look at the output of each gate, okay, when you look at the output of the top gate, it goes back to one of the inputs of the bottom gate, and vice versa. The output of the bottom gate goes back to one of the inputs of the top gate. And these are NAND 2 gates, okay, in case you haven't noticed, they're NAND 2 gates, because when you look at the symbol, it looks like an AND gate, which it is, but there's also a little bubble at the output, which means the output is negated. And that's why it's a NAND gate, a negated AND gate. Okay. Okay, is it making any sense right now when both inputs are zeros, the outputs will be all ones? Does it make sense? Okay, it does make sense, because with a NAND gate, if at least one input is a 0, the output is going to be a 1. Okay, so you just have to look up a truth table to figure that out. Okay, cool, not a problem. What if I turn one of these into a 1? If I turn this into a 1, what's going to happen to the configuration of all of these components?
It's going to become 1, 0.
Okay, if I turn /R into a 1, okay,
Turn that off, but it
then
will
both
also turn that.
inputs of the bottom NAND gate will be 1s,
Yeah, it'd be
which
zeros.
means the output of the bottom NAND gate is going to be a 0, right? So now we have a 0 here going back to the other input of the top NAND gate. But would that change the output of the top NAND gate? No, because the top NAND gate has another input being a 0. Okay, so that means we're going to change the output over here. /Q will go from a 1 to a 0, but Q itself is not going to change. Is that okay? All right. So let's check it out. So we'll click this. Sure enough, that's exactly what happened. Okay, that's kind of cool. What if I turn /S to a 0 at this point? In other words, what if I click here? What's going to happen? Let's try to analyze.
To a 1.
It's going to be 0.
Well, let's find out. So if we change /S from a 0 to a 1, okay? So you look at the input to this NAND 2 gate. There's still one input that is a 0. So that means the output of this NAND gate will continue to be a 1. Well, if the output of the top NAND gate continues to be a 1, then the bottom gate is not going to change, because both inputs to the bottom gate will still be 1s, so the output of the bottom NAND gate will still be a 0. In other words, when I change /S from a 0 to a 1, it would not change Q or /Q. Is that okay? Is that making any sense? Okay, let's check it out. And sure enough, it did not do a single thing. Okay, so try to remember this picture. Okay, this picture has both inputs being 1s, and Q is a 1, /Q is a 0. Okay?
So it depends upon which one you switch first. Then.
Exactly.
Oh.
And you use just the right word. Which word did you use?
Which one do you switch first?
No, before that.
It depends.
It depends. Okay, it actually remembers.
Remembers.
Yeah. So it remembers how it got into this particular state. So let's go ahead and flip it, okay? How do I turn Q to be a 0 and slash Q to be a 1? Let's figure that out. Let's see if we can reverse engineer. The effect that I want is Q to be a 0, slash Q to be a 1. What do I need to do at the minimum, okay, in order to accomplish that? Well, if I want Q to be a 0, I need both inputs to be 1s, right? Both inputs of the top gate to be 1s. Okay, so that means this wire needs to go from a 0 into a 1. How do I turn this wire in from a 0 into a 1? One of the input has to become a 0. Which one do I have direct control over? Slash R. So if I change slash R from a 1 to a 0, that will change Q from a 1 to a 0. It will also change slash Q from a 0 to a 1. Okay, so let's figure that out and see whether that works or not. So click this, and sure enough, it changed the states of the gates the way I described it. But here's the interesting part. What if I were to flip this slash R from a 0 back to a 1? What do you think is going to happen?
Nothing.
Nothing is going to happen, exactly. Because if I flip slash R from a 0 to a 1, nothing is going to happen because the bottom NAND gate has the other input being a 0. And it only needs at least one pin to be a 0, one of the input pins to be a 0, for the output to be a 1. So if the bottom gate continues to output a 1, then the top gate is not going to change. So let's make sure. Okay, none of the output has changed. But when you look at this configuration, it's the same input configuration, but yet the output configuration is different from last time. Are you guys noticing that?
So it's impossible for them both to be 1. Yeah, both the outputs to be 1.
Ah, that is a very interesting question. So the question now is, it seems like the output state has to do with what happened before both inputs become 1s, right? And we have explored the two possibilities. Okay, we have explored the possibility where slash S was a 0, and then we bring it back to a 1. We explore the possibility when slash R is a 0, and then we bring it to a 1. But we haven't explored the possibility when both inputs are both 0s, and then we turn both to 1s at exactly the same moment.
It's going to break.
Well, it's not going to break, okay? It will still behave in a certain way. The question is, what is the behavior if we are to do that?
So you'll hold the previous state.
No. It's going to get into what we call a oscillation mode.
Yeah.
It's going to get into oscillation mode. Okay, so let's just kind of go through this in our minds and imagine what's going to happen. Okay, so I'm going to change. Okay, I cannot actually simulate this, but I can kind of explain it. So imagine that both input pins switch from 1 to 0s at exactly the same moment. Okay, so then the input, one of the inputs to both NAND gates will go from a 1 to a 0 as a result. Okay, no big deal. But it takes a certain amount of time before that change affects the output of the NAND 2 gates. That is the key. Okay, so after a certain amount of time, some nanoseconds, then both gates will change at the same time. So both gates will update their output to be 0s, to be 1s. So you have one coming out of the top NAND gate, and you have one coming out of the bottom NAND gate. All right? Those ones, okay, are being fed back to the inputs, right? And then what's going to happen?
Yeah.
It will initiate the change of the gates changing. Okay, but from the moment that those changes occur, it will take a propagational delay for the actual output to become 1s. And they go back to 0, and go back to 1, go back to 0, go back to 1. So this circuit will start to oscillate. In other words, if you switch both input pins from 0 to both 1s at exactly the same moment, and the gates have exactly the same propagational delay, then you observe the output switching between 0s and 1s. And the period of that switching is going to be 2 times the propagational delay of the NAND gate.
So as a computer, actually that probably wouldn't be an issue because you would never have it be exact.
Well, that's a very good question. So the question is, what if one gate is long, it takes a longer amount of time to update, and the other one doesn't take as much time, right? So in that case, it would actually settle in a particular state. It wouldn't oscillate anymore.
So then how do your computer prevent this from happening?
You simply do not go from both inputs of 0s to both 1s at the same time. that's the bottom line is that. Okay? So now the question is, if when you're designing these circuits, okay, when you're actually doing the VLSI design on a chip, okay, you may not be able to predict the exact latency of all of these gates. So if you design one of the gates or one of the NAND gates to have at least twice the propagational delay of the other one, then you won't actually have an oscillation anymore. It will actually settle to one particular state. So now, it means the actual behavior of this circuit depends on propagational delays of the individual gates. And what in hardware design, it is called a race condition.
What?
A race condition, RACE race. It depends on who gets to the finish line first. And that is usually not a very bad problem to have. When your hardware has a race condition, it usually is a bad situation. Most of the time, that kind of bad situation means the computer hardware that is involved would not work in certain conditions. Like when you heat it up, it will start to behave differently, because when you heat it up, transistors will change their actual latency. Okay, temperature can change that. The interference can change that. Whether you put that thing close to a microwave oven may change that. Okay, so that's a bad situation because your computer can lock up and not work anymore. But the worst problem is the race condition leading to security issues. Okay, so I'm pretty sure some of you have heard of Meltdown and Spectre.
Right.
Oh yeah.
Mm-hmm. And
Microsoft's getting sued, I think, or something.
And Heartbleed.
And Heartbleed, but Heartbleed is a software issue, it's not a hardware issue. These two specifically are the hardware issues. So when you click on,
Intel released a patch, it didn't work.
so that Microsoft had to roll it back.
Mm-hmm.
Yep. So when you look up this, you don't need to read the entire thing, but you will see the summary basically talks about how these two are based on hardware race conditions, which basically has to do with, you have two paths that are going in parallel, but which path, quote unquote, takes a shorter amount of time determines the outcome. Okay? In this particular case, the race condition has to do with the engineers basically overlooking a certain issue with caching. So the question is, can I read the cache before the protection mechanism kicks in and say that, no, you're not supposed to read that? Okay, that is the race condition that's causing, well, in a few words, that is causing the security issue. So people can structure their instructions in a way so that the caching mechanism can disclose the content of memory locations before the protection mechanism kicks in and go like, no, you're not supposed to look at that. And that leads to security issues. So, but this kind of security issue is much worse than, what was the other one? Heartbleed. Because Heartbleed is an open SSL coding issue. If your web server is not using OpenSSL, you don't have a problem. Okay? This affects every single computer. that is using these kinds of processors. It doesn't even matter what operating system you're using. You can be using an Intel processor on a Mac OS 10 operating system. It's affected. You may be using Linux. It's affected. Using Windows, it is also affected. So that's why these issues become a bigger issue compared to Heartbleed, which is a software issue, because it impacts multiple operating systems at the same time. Okay, and it's all because of a race condition. So the relevancy of mentioning this has to do with the circuitry that we just analyzed. Okay, this one here, depending on the latency relative latency between these two gates, the behavior can change. If they're identical, they oscillate. But if they're not identical to a certain point, it doesn't oscillate anymore. Okay? So if you are a hardware engineer, okay, and you design something like this, and you did not take into consideration that this circuit may get into a state that it will start to oscillate, and just because of pure luck, okay, the first time you fabricate this onto an actual processor, the gates are completely asymmetric to the point where it doesn't oscillate, okay? So now the asymmetric nature of your actual silicon version of your implementation is masking the issue. Okay, so the issue is still there, but it's being masked. Yep.
So basically one pathway would be longer than the other pathway.
Yeah, it has to be at least twice as long
Okay.
in order for it not to oscillate.
Okay.
Because otherwise, it will still kind of catch and then start to oscillate. I can be incorrect here. I have to do another analysis to find out exactly when it will not oscillate. But I know for sure that the length of time of update will change the behavior to the point where it doesn't oscillate anymore.
Okay.
Okay. So by pure luck, your circuitry may not have a problem, may not exhibit any problem. Okay. But when later on, when you change the die size and when you change the transistor size, it may change the timing, right? And then your race condition will start to show up. In other words, by shrinking the size of your transistors, which is going to happen, the problem may show up one day. And then you'll be scratching your head and go like, I wonder what happened to my design, because it used to work and now it's not working anymore. I didn't change a single thing. It's because this problem was masked by the manufacturing fabrication process. So how do you think I knew about these things? I'm not smart enough to come up with these scenarios.
Isn't this Newman?
Well, because I've been bitten by something like this before. Okay, so another 3 minutes of this story, but it's actual story. Okay, it actually happened in the past. So I used to work for a company in Davis called Zero. It became Digi. These days it was bought by Digi. So anyway, so one day I got a call from the customer service department and go like, every single board that we ship out is not working anymore. And our customers are screaming. They're just totally unhappy about our products. Okay, so what changed? So we couldn't figure out anything that got changed. The firmware was not changed. Software was not changed. So when we look at all the components, nothing was changed. And then somebody noticed the date stamp on the chips changed. Okay, so so let's say we went from October 2016 to December 2017, something along that line. Okay, because all the chips have a date code on it. So, and we noticed that the problem only shows up on boards that has a chip of the newer date code. All the ones with the older date code was not affected. Okay, so we go like, okay, that's really odd. Okay, and I was the software engineering department head at the time. My boss used to tell me that I'm the director of software development. It's a big title. Okay. Which usually means you have all the responsibilities. If something goes wrong, you are in charge now. So I just call myself, no, just call me I call myself one of 7 at the time, like Borg.
Yeah.
I was the first software engineer, so that's why I was called one of 7. So I was responsible to figure this out. So as it turns out, it was a software issue. The software issue had to do with in the manual, it specifically say, update this register first, and then update that register. It should be in this particular order. Okay? And then whoever wrote that code, and I knew exactly who that was, whoever wrote that code decided to flip the order. But because the older die design, okay, so when you use the correct order, it has internal lock circuit to make sure a race condition does not happen. Okay? But when you flip the order of updating those particular locations, then race condition can happen. So the older die using bigger transistors masked the issue. The race condition was in favor of the quote-unquote correct sequence. The new date code indicated that, later on when we looked it up, the new date code indicated that they changed the die process. They changed the transistor size from one size to a smaller size, and that changed the timing enough so that that race condition now favors the other side, the wrong side, so to speak. So the software issue, happens. It took me 3 days to find out, which 2 instructions was reversed and was responsible for that particular bug.
Wow.
Yep. So I'm not sure, how much of this you guys, actually, understand, because there's a lot of technicality in it. But the whole point is race conditions is important. It happens in real life, and it can have a lot of major impact to devices. Yep.
So I'm guessing there's no actual hardware way of fixing it other than to make it asymmetrical.
To fix this?
Yeah.
Well, to fix this, you basically have to make sure that you do not have a scenario that both inputs will go from 0s to 1s at the same time. So you have to fix the source of the issue and not the symptom of this particular problem. And there are ways to make sure that you cannot have both inputs going from 0 to 1s at the same time. The thing about the SR latch is it usually is not used by itself. It serves as a component in larger memory devices. So when you design the larger memory devices, you have additional circuitry to make sure that that does not happen. So we'll see next week, after exam 1, on Wednesday hopefully, we'll see how this SR latch design is actually utilized in other bigger memory devices called flip-flops. So we'll get to D flip-flops next week. They're all in the module, so if you have time, especially after exam 1, please read ahead of me, because this stuff takes time to absorb. Because the analysis of the circuit is different from what we are used to, because of the feedback mechanism. All right, so I'm going to stop the lecture at this point. We'll move on to the lab, and then the earlier part of the lab is going to have a little bit of demonstration first, because I want to show you guys how to